Hi everyone, my name is Marina, and in this video, I'm excited to give a brief overview of our work, PikeLPN, Mitigating Overlooked Inefficiencies of Low Precision Neural Networks. Before I start, I would like to thank all of my co-authors who made this work possible. So first, low precision quantization is known to significantly improve the energy efficiency. So for example, an int8 multiplication consumes 18x less energy than floating point multiplication, and similarly for addition, it consumes 30x less energy than floating point addition. And this is obviously beneficial in data centers because it reduces its cost of operation, and it's also beneficial in setups like edge devices because it leads to a longer battery life. In this paper, we performed a deep analysis into the energy consumption of state-of-the-art low-precision models and the arithmetic operations they involve. So first, we have the multiply accumulate operations in layers such as convolution, linear layers, and attention layers. This is where most of the research effort on quantization goes. But then there are also element-wise operations in layers such as batch normalization, activation functions, and also those quantization-specific parameters for scaling. Those operations are always left unquantized in state-of-the-art models. This figure here shows the contribution of both quantized multiply accumulate operation and non-quantized element-wise operations to the arithmetic energy consumption at different precision. And we can see that for full precision models, the cost is dominated by the multiply accumulate operations, but it keeps going up for lower precision models, reaching almost 90% of the total cost in binary models. Now, the problem is that existing cost metrics only account for multiply accumulate operation and leave out the element-wise operation, which misleads anyone who uses those metrics to guide their design process for low precision quantized models. This brings us to the first part of our solution. So guided by the insights from our analysis, we introduce a novel cost metric, ACE-V2, which uses a lot of concepts from the original ACE metric. ACE-V2 provides a simple formula, as shown in this table, for different arithmetic operations like addition, multiplication, and shift, which are commonly used in quantized models. And we found that ACE-V2 has a correlation of 0.99 with the independently measured energy consumption. Next, guided by our ACE-V2 metric, we design a novel family of low-precision efficient models. We start with a simple MobileNet-like architecture. The main building block has a separable convolution layer, which consists of a depth-wise layer and a point-wise layer with some activation and normalization layers in between. Now, trying to quantize this compact model, including both the element-wise operation and the multiply accumulate operation, we introduced three novel quantization strategies. The first one is batch norm quantization, which were usually left unquantized in the past because they are very sensitive to quantization. And then we also introduce a distribution heterogeneous quantization, which we use to mitigate the distribution mismatch of the pointwise and the depthwise layer in the separable convolution block. And also we introduce a double quantization strategy where we quantize the quantization parameters themselves to further reduce the cost. More details about those quantization techniques can be found in our paper. Now to show a quantitative result of how PikeLPN performs. So this figure here shows the ACE-V2 cost on the x-axis and the accuracy on the y-axis. We can see that our PikeLPN models achieve a Pareto optimal performance compared to other baselines. Those baselines are mostly binary models from literature, and we meant to include them here to show how efficient our model is. And our conclusion is PikeLPN can actually outperform 1-bit state-of-the-art neural networks like PokeBNN. So to summarize our contribution, we first analyzed the overlooked element-wise operation costs in state-of-the-art models and state-of-the-art cost metrics. And then we propose a novel hardware agnostic cost metric, ASV2, which has an 0.99 correlation with energy consumption. And finally, we propose PikeLPN family of low precision models with up to 3.5x energy improvement compared to state-of-the-art binary models. Thank you for listening to our video. And if you are at CVPR, please stop by our poster.